Microchips are everywhere. These tiny, intricate pieces of technology have become an integral part of our daily lives, seamlessly embedded in the devices we use every day. They are in our phones, enabling us to connect with the world, access information at our fingertips, and stay in touch with loved ones. They are in our cars, making driving safer and more enjoyable with advanced navigation and entertainment systems, and even in our toasters, ensuring our breakfast is perfectly browned every morning. These tiny electronic brains power our modern world, driving the functionality of countless devices and systems that we often take for granted. But have you ever wondered how these marvels of technology are made? The process is a blend of art and science, involving numerous steps and incredible precision. The journey of microchip manufacturing is a fascinating one, involving incredible precision and cutting-edge science. It starts in high-tech laboratories where scientists and engineers work tirelessly to push the boundaries of what's possible. It all starts with a humble material, silicon. This element, found in abundance in the Earth's crust, is the foundation of all microchips. Silicon is found abundantly in sand. The grains of sand on a beach might seem insignificant, but they hold the potential to become the building blocks of our digital world. We extract silicon from sand and purify it to an astonishing degree. This purification process is crucial, as even the smallest impurity can affect the performance of a microchip. In fact, the silicon used in microchips is some of the purest material on Earth. The purified silicon is then transformed into wafers, which serve as the canvas for creating intricate circuits that will eventually become microchips. Silicon's abundance and unique properties make it ideal for microchips. The journey begins with sourcing silica sand, often found in specific regions known for its purity. This sand undergoes extensive processing to extract the silicon within. The raw silicon is then chemically refined to remove impurities. This process involves multiple stages of heating, melting, and cooling. The result is a polycrystalline silicon material still not pure enough for microchip fabrication. Further purification is needed to achieve the exceptional purity required. To create the perfect base for microchips, we need a single continuous crystal of silicon. This is achieved through a process called Czochralski crystal growth. In this process, a seed crystal is dipped into molten silicon. The seed crystal is slowly pulled upwards while rotating. As it does, it pulls molten silicon with it, gradually forming a large cylindrical single crystal called an ingot. These ingots can be several feet long and perfectly uniform, a testament to the precision of modern engineering. Once the silicon ingot is grown, it's sliced into thin, round wafers. These wafers are incredibly thin, often less than a millimeter thick. They need to be extremely flat and smooth for the next stages of manufacturing. To achieve this, the wafers undergo a meticulous polishing process. They are polished using specialized machines and chemical slurries. This removes any imperfections and creates a pristine surface ready for the intricate process of circuit creation. Now comes the crucial step of creating the actual circuits on the silicon wafer. This is where photolithography comes in. Photolithography is like photography, but instead of creating images, we use it to print circuits. A photosensitive material called photoresist is applied to the wafer. Then a machine called a stepper shines ultraviolet light through a mask. This mask contains the blueprint of the circuit pattern. The exposed photoresist hardens, while the unexposed parts remain soft. After exposure, the wafer is washed to remove the soft photoresist. This step is crucial as it ensures that only the areas that were not exposed to light remain covered by the photoresist. The washing process is meticulously controlled to avoid damaging the delicate patterns that have been created on the wafer's surface. This leaves behind the hardened photoresist, forming a protective layer that replicates the circuit pattern. The hardened photoresist acts as a mask, safeguarding the underlying silicon during subsequent processing steps. This precise replication is essential for the functionality of the final microchip. The exposed silicon is then etched away using chemicals. This etching process removes the unprotected silicon, creating the intricate structures needed for the microchip's operation. The choice of chemicals and the etching duration are carefully optimized to achieve the desired dimensions and shapes. Next, we introduce impurities called dopants to specific areas of the silicon wafer. These dopants are introduced in a controlled manner to alter the electrical properties of the silicon, enabling the creation of various semiconductor devices. This process, called doping, modifies the electrical properties of the silicon. By carefully selecting the type and concentration of dopants, we can create regions within the silicon that have different electrical characteristics which are essential for the functionality of transistors and other components. Ion implantation, a more precise method, is also used to introduce dopants with high accuracy. This technique allows for the precise control of dopant placement and concentration, which is critical for the performance and reliability of the final microchip. These processes are crucial for creating transistors, the building blocks of microchips. Transistors act as switches or amplifiers in electronic circuits, and their precise fabrication is essential for the performance of modern electronic devices. The combination of these advanced techniques ensures that each microchip meets the stringent requirements of today's technology. A microchip has multiple layers of circuits and components. To create these layers, we repeat the photolithography, etching, and doping processes multiple times. Between each layer, new materials are deposited onto the wafer. These materials can be insulators, conductors, or semiconductors, each serving a specific purpose in the final chip. This meticulous layering process, repeated dozens of times, creates the complex three-dimensional structure of a modern microchip. Once all the layers are complete, the wafer undergoes rigorous testing. This is a critical phase in the microchip production process, where each layer's integrity and functionality are meticulously examined. Advanced machinery and skilled technicians work in tandem to ensure that every aspect of the wafer meets the highest standards. The cleanroom environment is essential to prevent any contamination that could compromise the microchip's performance. Each individual chip on the wafer is tested to ensure it functions correctly. Engineers use powerful microscopes and precision instruments to inspect the microchips at a microscopic level. Robotic arms and automated systems play a crucial role in this process, allowing for high-throughput testing and ensuring that each chip meets the required specifications. Any defects or anomalies are identified and addressed at this stage, ensuring only the best chips move forward. Then the wafer is cut into individual chips, each a tiny masterpiece of engineering. This dicing process requires extreme precision as the chips are incredibly small and delicate. Specialized saws and cutting machines are used to slice the wafer into perfectly sized chips ready for the next stage of production. The precision of this process ensures that each chip remains intact and functional. These chips are then packaged in protective casings with tiny wires connecting the chip to the outside world. The packaging process is vital to protect the delicate microchips from physical damage and environmental factors. Technicians carefully place each chip into its casing, ensuring that the connections are secure and reliable. This step also involves rigorous testing to confirm that the packaged chips will perform as expected in real-world applications. These packaged chips are what we find in our electronic devices. From smartphones to computers, these microchips are the brains behind our modern technology. Once packaged, the chips are carefully inspected one last time before being shipped to manufacturers around the world. This ensures that every chip that reaches the consumer is of the highest quality and ready to power the next generation of electronic devices. The journey from a grain of sand to a powerful microchip is complete. This transformation is a testament to human ingenuity and technological advancement. Each step in the process, from raw material to finished product, involves a combination of cutting-edge technology and meticulous craftsmanship. The result is a tiny yet powerful component that drives the digital age. And as technology advances, the future of microchips promises even smaller, faster, and more powerful devices that will continue to revolutionize our world. Researchers and scientists are constantly pushing the boundaries of what is possible, exploring new materials and innovative designs. The next generation of microchips will enable breakthroughs in fields such as artificial intelligence, quantum computing, and beyond, shaping the future in ways we can only imagine.